Welcome to the full solutions of lesson 7 of vectors, which covers 3D vectors. Okay, for the first question, we are asked to determine the value of k here for a unit vector A, and vector A has x components of 1 over 4, y components of k, and z components of negative 1 over 3. Okay, we know that a unit vector has length of 1, so that means the magnitude of vector A is going to equal to 1. And that is also equal to the square root of the x component squared, so that's 1 over 4 squared plus k squared plus negative 1 over 3, which is the z component squared. I will continue this side. 1 is equal to roots 1 over 4 squared, I'm going to square the numerator. 1 squared is 1, and 4 squared is 16. So 1 over 16 plus k squared plus negative 1 squared is 1, and 3 squared is 9. I will then square both sides, and we'll end up getting 1 on the left-hand side, and that's equal to square root of that squared cancels the root sign, and I get 1 over 16 plus k squared plus 1 over 9. I want to isolate for k squared over here, so I will start moving the 1 over 9, or I will subtract both 1 over 9 and 1 over 16 from this side. So I will write my step here. And I will get k squared. I'm going to rearrange things a little bit. Is going to equal to 1 minus 1 over 16 minus 1 over 9. A common denominator to the right-hand side here is going to be 144. And I have, no, this is 1 over 1, so the denominator is multiplied by 144, numerator is going to be multiplied by 144. For this one, 16 is multiplied by 9 to get this, so 1 times 9 is 9. And for the last one, numerator is multiplied by 16, so, sorry, denominator is multiplied by 16, so the numerator is also going to be multiplied by 16. So then k squared is equal to, when we do 144 minus 9 minus 16, we will get 119 over 144. I'm going to continue here. I'm going to square root both sides, and I will get k is equal to plus or minus square root of 119 over 144, and I will rewrite this as root 119 over root 144, and I can simplify the denominator. Root 144 is 12, and my numerator stays as 119. This is my final solution. The second question tells us to determine the values of x, y, and z if vector AB is equal to vector AC. So let's do this. Vector AB is going to equal to the x component of vector B minus x component of vector A. That's negative 2 minus negative 2, and 0 minus 3 for the y component, and 5 minus 1 for the z components. This is going to equal to negative 2 minus negative 2 is going to equal to 0, negative 3, and 4 as my x, y, and z components. Vector AC is going to equal to the x, y, and z components of vector C, which are simply x, y, z, and I'm going to subtract them by the x, y, and z components of vector A, which are negative 2, 3, and 1. Once I have this, I'm going to simplify this. X minus negative 2 is x plus 2. I got y minus 3 and z minus 1. We know that vector AB is going to equal to vector AC, meaning that 0, negative 3, and 4 is equal to x plus 2, y minus 3, and z minus 1. Now, I'm going to use a highlighter to show you the different sections of this. So we got 3 different equations here. My first equation says x plus 2 is equal to 0. Second one says y minus 3 is equal to negative 3. And the third one says z minus 1 is equal to 4. For the first one, I'm going to subtract 2 from both sides. X is equal to negative 2. For the next one, I'm going to add 3 to both sides. Y is equal to negative 3 plus 3, which is 0. And for the last one, I'm going to add 1 to both sides. So z is equal to 4 plus 1, which is 5. And this is my final solution because all it's asking for is for us to determine the values of x, y, and z. For the next question, we are given that ABCD is a parallelogram and we need to determine the coordinates of D given that given points A, B, and C. Let's draw a parallelogram. And it doesn't matter which way we are going to label the points. I'm going to do them as A, B, C, D. It does matter that we go either clockwise or anti-clockwise. So it has to be A, B, C, D or A, B, C, D. We can't go A, B, C, D and randomly put them. They have to be in order. In terms of the points, we have point A, we have point B, and we have point C. We need to find point D. There are different ways of doing that. One way to do it is we know that vector BC, this one over here, is going to equal to vector AD, and that is because in a parallelogram, these two sides, the opposite sides, are equal in size and they're also parallel, meaning that their direction is the same and their magnitude is the same, which is what two equivalent vectors are. So we are going to use that concept and we are going to say that vector BC is going to equal to vector AD. We can find vector BC. I'll do that separately here. And I'm going to write vector BC. We have points B and C. So the x, y, and z components of C are 3, 0, 1. I'm going to subtract them by x, y, and z components of B. So 1, 1, and negative 1. And this is going to equal to 3 minus 1 is 2, 0 minus 1 is negative 1, and 1 minus negative 1 is 0. For vector AD, I'll write that one here. I'm going to have the x, y, and z components of point D. I don't have them, so I'm just going to write them x component of D, y component of D, and z component of D. D minus the x component of A, which is negative 2, the y component of A, which is 1, and the z component of A, which is 4. I know that vector A, I'm going to use a highlighter here. We know that vector BC and AD are the same, and that means that this is equal to this. So this is equal to this. So basically that means that xd minus negative 2, yd minus 1, and zd minus 4 is equal to 2, negative 1, and 0. And we don't have to write all these steps. I am writing a little bit more steps here for you folks to be able to see everything, these will make three different equations. The first one is xd minus -2 is equal to 2. Second, yd minus 1 is equal to -1. And lastly, zd minus 4 is equal to 0. For the first one, this is same as xd plus 2 is equal to 2. So I'm going to subtract 2 by both sides, and I will get xd is equal to 0. For the second one, I'm going to add 1 to both sides. So yd is equal to -1 plus 1, which is equal to 0. Interesting. And the last one, I'm going to add 4 to both sides to get 4. So for point D, the x component is 0, the y component is 0, and the z component is 4. And that is my final answer. We can do a quick check to see if our final answer is correct or not, and we can also we can do this using these two other sides over here. We could have used these sides in the beginning as well, but in this question we also know that vector CD is equal to vector BA because they're opposite sides of a parallelogram, meaning that they have equal sizes and they move in the same direction. So in this case, vector CD needs to equal to vector BA. Vector CD, I'm going to take the x, y, and z components of vector D, 0, 0, 4, and I'm going to subtract them from vector C. That's 3, 0, 1. And we are going to check that one. That one's going to be -3, 0, 3. And we're going to do vector BA. So this is BA, and this is CD. So vector BA, I'm going to take the x, y, z components of vector A, and I'm going to subtract them by the x, y, z components of vector B, which are 1, 1, and -1. This is going to give me -2 minus 1 is -3, 1 minus 1 is 0, and 4 minus -1 is same as 4 plus 1, which is 5. Well, this is great. We can see that they're actually not equal. The x components are correct. The y components are correct. But there's something wrong with what we've done for the z component. So we have to go back and check our steps. So we're not going to worry about x and y components here. For the z components of BC, we have 1 minus -1. That does not equal to 0. That actually equals to 2. So I'm going to cross that and change it to 2. And for everything else, it seems correct. So I'm going to change this to 2. And this equation changes here. This is going to be changed to 2. And when adding 4 to both sides of here, I'm going to get 6. So this is going to end up being 6. Going back to CD, I have my components 0, 0, and 4. Instead of 4, I'm going to use 6, and 6 minus 1 equals 5. So my final answer for D actually equals to 0, 0, 6. And this is why it is so important to go back and check your solutions. For the last example in this video, we're asked to identify the type of triangle formed by connecting these 3 points. So let's do that. So as we talked about this before, we need to, actually I'm going to draw this out. We don't know how it looks like, but I'm going to draw a random triangle. It's going to be A, B, C. And to figure out what kind of triangle we have, we need to figure out the sides of all of the sides first. If all of the sides are the same, we got equilateral. If 2 of them are the same, then we have an isosceles, and we got an scalene triangle if all of them have different sides. And once we have the sides, we also have to use Pythagorean theorem to check to see if the triangle is a right triangle or not. So let's get started. To find the magnitude of vector AB, first we need the vector itself. So we are going to use the x, y, and z components of point B, which is -3, 5, and 2, and we're going to subtract it by x, y, and z components of vector of point A, which is 1, 2, and 1, and -3 minus 1 is -4, 5 minus 2 is 3, and 2 minus 1 is 1. We're going to do that for all of the vectors, or we're going to find all the vectors. So BC, for this one, we're going to use the x, y, and z components of point C, -1, 1, and 2, and subtract them by the x, y, and z components of point B, which are -3, 5, and 2. -1 minus -3 is -1 plus 3, which is 2. 1 minus 5 is -4, and 2 minus 2 is 0. Finally, for vector AC, I'm going to take the x, y, and z component of point C, which are -1, 1, and 2, subtract them by x, y, and z component of point A, which are 1, 2, and 1. We get -1 minus 1 is -2, 1 minus 2 is -1, and 2 minus 1 is 1. Okay, let's find the magnitude of each vector here. So AB is going to be root of -4 squared, that's the x component, plus the y component squared, plus the z component squared. That is going to be 16 plus 9 plus 1, which is going to equal to root 26. For vector BC, we are going to do root 2 squared plus y component squared plus z component squared, so that's root 4 plus 16, which is root 20. Finally, for the last one here, we have, oh sorry, this was also the magnitude. The magnitude of AC is going to equal to root, and we got the x component squared plus the y component squared plus the z component squared, and that is going to equal to root 4 plus 1 plus 1, which is root 6. Basically, we can see that we can actually write it out. AB, the magnitude here is root 26. For BC, the magnitude is root 20, and for the last one, it is root 6. And I haven't simplified any of my values in terms of roots yet, but I will do that a little bit later. Okay, I know that all the magnitudes are definitely different, so this is in a scaling triangle, but we also need to check using Pythagorean theorem whether the triangle is a right triangle or not. So here I have root 26, that's the largest side over here, so we are going to check to see if root 26 squared, the hypotenuse squared, is equal to the sum of the two other sides, the square of the two other sides. So root 20 squared plus root 6 squared. Is it equal? So root 26 squared is 26. And does that equal to root 20 squared, which is 20, plus root 6 squared, which is 6? And it is. So this test here says that this is a right triangle. So for our final answer, first of all, this one I'm also going to write this as root 2 root 5 as the simplification, because that's root 4 root 5, which is equal to 2 root 5. That's the most simplified radical form. So For my final answer, I am going to write that since a magnitude of AB does not equal to the magnitude of BC, and that does not equal to the magnitude of AC, and since, in this case, AB squared is equal to AC squared plus BC squared. So this one is, so this test is to figure out what type of triangle in terms of scalene, isosceles, or equilateral, and this one is to test for right angle triangle. Therefore, this is a right triangle and scalene triangle. And this is our final solution.